Hello, my name is Ian Campbell, and today I will discuss the determination of polymer composite interface mechanical response. New and exciting composite materials are becoming increasingly utilized for structural applications due to their combination of strength and toughness. For example, the biomedical industry has turned to composites to design prosthetics and artificial tissues. Additionally, favorable strength-to-weight ratios allow 50% of the Boeing 787 aircraft to be constructed using composites, as indicated by the blue regions in the bottom image. To accurately tune the properties of novel composites, especially polymer nanocomposites, it is important to understand the properties of the composite interface. The interface is the region of bulk material with unique properties immediately surrounding each hard inclusion particle. The interface spans tens to hundreds of nanometers, and as such, its significance increases with the particle's surface-to-volume ratio. Previously, my advisor's group used nanoindentation and finite element analysis, or FEA, in order to determine interface properties. An atomic force microscope, or AFM tip, was used to measure the force needed to deform a laminar composite in an array of locations. Mechanical properties, such as the normalized modulus shown in the plot to the right, can be backed out of the force measurements. However, these results are convoluted by stress concentrations due to the hard substrate shown by this FEA model, which does not include an interface. Only by utilizing these substrate stress concentration contributions in gray to deconvolute the experimental results in blue can the true interface properties in red be determined. While successful, these results are made uncertain by the complex state of stress imposed on the sample by indentation, and by the similarities between the size of the indenter tip and the span of the interface region. My goal is to emulate the deconvolution used with nanoindentation for a mechanical test which causes a less complicated state of stress, specifically uniaxial tension. Previously, microtensile tests have been used to study the local mechanical properties of nanocomposites using the experimental setup shown here. AFM was implemented concurrently with digital image correlation to calculate strain fields shown here superimposed over an optical image. In this case, the lack of homogeneity in strain fields around each inclusion is recognizable in the different shading to the right and left of the circled particle. The result was an inaccuracy in the measurement of local mechanical properties. These inhomogeneities can be explained by interpreting the strain fields as both a function of the mechanical stress concentrations around a particle and the property differences across the interface gradient. Determining the interface properties requires the deconvolution of these two factors. Deconvolution requires at least two FEA models, one with and one without a distinct interface region. This plot shows artificial data for the change in modulus over distance from the particle. As an example, it is apparent that if the data from the model with no interface in blue is subtracted from the corresponding data for the interface model in red, the programmed properties shown by the orange rectangles are returned. The true function, which relates the interface and no interface models, or stress concentration and interface gradient, may be more complicated than the subtraction shown, but determining such a relationship is the goal of my work. I began by creating an FEA model of a polycarbonate matrix with one alumina particle in the center. The left edge was fixed, and tension was applied to the right edge. The bulk matrix was given elastoplastic properties defined by the Young's modulus, tangent modulus, and yield stress indicated by this stress versus strain curve. Contacts between bodies are bonded, and a 2D plane stress condition was used for these initial simulations in order to compare results to numerical solutions. This base model is representative of a nanocomposite without an interface, or no IP, and is used to determine the contributions of stress concentrations to the stress recorded at given locations upon the application of tension. To add an interface, I created a second model with 4 polycarbonate rings around the interface, each spanning 50 nanometers. The conditions of this simulation, including the interface, or IP, is identical to the no IP case, except that each ring is given a unique elastic modulus, tangent modulus, and yield strength depicted by the plot in the bottom right. Ring 1 describes the ring closest to the particle, and ring 4 describes the furthest. When combined with the no IP model, measurements taken from this simulation help to identify the effect of an interface gradient on the mechanical response. From these FEA models, I plotted the normal stress against global strain for each ring and the far field matrix. Each curve was produced following the schematic in the lower right. Measurement sites, each composed of 5 points, were centered in each ring, and the normal stress was calculated as the average of the 5 points over a range of strains. The measurement zone was situated at 0 degrees with respect to the x-axis, or the r-axis, as the stress fields around a circular particle vary with both r and theta. The chosen location further simplifies the state of stress as theta is 0. A similar plot can be produced for the no-IP model using the same measurement zone. The IP model represents a convoluted dataset, or the experimental stress fields observed at the interface, and the no-IP model demonstrates the mechanical stress concentrations. Some combination of the two results should yield the input properties at any given point. Upon initial comparison, it is evident that the two plots have opposite trends. At relatively larger strains, it is clear the stress experienced increases with distance from the particle in the IP model and decreases with distance in the no-IP model. To further examine the significance of the stress versus strain trends, linear regression was used to estimate the slopes of the elastic and plastic portion of each curve in both models. Both the elastic and tangent moduli of each ring are plotted. The orange squares represent the programmed properties and are included for reference. Unlike the artificial example, a relationship between the IP and no-IP models that returns the input properties is not easily discernible from these plots. One possible explanation for this complexity is the mechanical stress concentrations caused by each interphase ring, which are unaccounted for in the current models. Determining the deconvoluting relationship will be challenging and will likely require the development of further models. Additional models are helpful for deconvolution as they can be used to determine the relative impact of simulation parameters on the resulting stress fields. I created variations of the original IP model in which I altered different conditions. The first such variation I created was a model in which the size of the interface rings was not constant. Each ring in the original model was 50 nanometers in length, but the ring spans in this altered model increase from ring 1 to ring 4, as indicated in the upper right. The resulting stress-strain curves for each ring are shown in the lower right next to the original results for comparison. Notice that the measurement sites were adjusted for this altered model so that they would still be situated at the center of each ring. Comparing the resulting stress-strain curves to the results of the original IP simulation shows few differences. This indicates that the span of the interphase rings has little effect on the experienced stress. The next modified simulation I designed was created by changing the magnitude of the interphase gradient. The elastic moduli and tangent moduli of each of the interphase rings were adjusted such that the moduli of ring 1 were increased the most, the moduli of ring 2 and 3 were moderately changed, and the moduli of ring 4 were held constant. These changes are evident in the plots of the new input constitutive relationships shown in the bottom right. If the results of this new model are compared to the original model, it is evident that altering the moduli of the interphase rings affects the stress response, as is most apparent in these regions of the plots. The differences in stress response of the IP model caused by variations in the moduli can be studied more easily by plotting the data for each ring against its counterpart from the new model. For example, the upper left graph plots ring 1 from the IP model against ring 1 from the model with high moduli. It is important to note that increasing the moduli decreases the stress experienced, as expected, and that this effect becomes more prominent at larger strains. In conclusion, to determine the local interphase mechanical properties and parse out the different contributions to experimental tensile stress and strain fields such as these, comparison of multiple FEA models is required. Also, I can conclude that simulations beyond the no IP and IP conditions will likely be needed to reliably deconvolute experimental data. Initial results from one such additional simulation suggest that the magnitude of input properties is an important contribution to the role of the interphase gradient, and that deformation to larger strains may cause differences between models to be more identifiable. Moving forward, more models will be produced with particle size and particle shape varied to identify additional significant parameters for deconvolution. I would like to acknowledge and thank Dr. Pavan Kaluru for his mentorship and support, as well as his students for their assistance and constructive criticism. I would also like to acknowledge and thank Texas A&M's online O-REU program, as well as Texas A&M HPRC and CREDS for their sponsorship, funding, and access to resources. Thank you very much for your attention, and feel free to reach out to me with any comments or questions.